Hey everyone, welcome to today's lesson on intermolecular forces. This is our 7th lesson in Unit 6. So today we have kind of two basic goals or two learning targets where we want to be able to list the types of intermolecular forces that we see occurring between molecules, and we also want to be able to predict relative phase change points based on the intermolecular forces that are present. Now, on day 2, on our atoms, molecules, and particles lesson, this topic of intermolecular forces came up as we were differentiating between separating molecules or separating atoms that were bonded within the molecular structure. And so what we're going to be talking about today with intermolecular forces is we're looking at the force of attraction that occurs between two molecules. And if your teacher is asking you to submit your notes, we'd love for you to take notes along with us, either using Cami, or you can print out this guide and write on your own sheet of paper, or write on top of it, or write on your own sheet of paper. So if you are going to take notes per request of your teacher, now is a great time to go ahead and start. Alright, but anyways, so intermolecular forces are forces of attraction between two molecules. The word inter means between, and then molecular is referring to molecules. So we're looking at some type of interaction or attraction that happens between different molecules. Now, because this is kind of a big word, we're sometimes going to abbreviate it using IMFs. So that stands for intermolecular forces. All right. Now, a quick note that's kind of going to be a big point for us this year as teachers. Never, 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 ever use the word bond when talking about intermolecular forces. The reason for that is the bond is what's known as an intramolecular force that is joining two atoms within a molecule. So that word intra, or prefix rather, means within a molecule. So an intramolecular force, which is very strong, it's hard to break, is a bond. An intermolecular force, that comes between separate molecules, and that is a weaker force than a bond within one molecule. So please keep in mind here that we are talking about forces in this lesson, intermolecular forces, and not a bond. We'll come back to bonds later in the semester, but for right now, I want you to really think about we're talking about the interaction between molecules, not the bonds within them. So make sure you put a big star by this box here. All right. So what we're going to find out is that the strength of attractions between molecules is going to affect a lot of the way that those molecules behave. And one of those ways is in how they change phases from solids to liquids to gases. So let's make a couple observations, if we could here, via a simulation. So what we have in this simulation is we've got some molecules that are just kind of represented as single particles. And we're going to be able to manipulate the attraction between the atoms, from weak attractions to strong attractions. So let's go ahead and start the simulation. Now, when the attractions are strong, you'll notice that that has a greater correspondence to the solid state of matter. The things are more close and compact. So we see there are stronger attractions in a solid. When we begin to weaken the attractions, we see that our molecules begin to take on more of a liquid state, where they still have some attractions, but they're able to move more freely. Now, if we continue weakening the attraction, that resembles more of a gas state. So the less attractions you have between molecules, the less intermolecular forces, and the more gas-like that substance will be. So let's see if we can fill that in on our notes. So what we see is that the solids, this is where you have the highest forces of attraction. And the gas is where you have the weakest forces of attraction. And while I'm at it, I'm going to change this word highest to strongest just for consistency here. All right. And so what we see as we go from solid to liquid to gas is that we are gradually weakening the attractions. And that's what has to be overcome in order to accomplish a phase change. Energy has to be applied, and what that energy goes into is weakening those intermolecular forces, those attractions between molecules. Now, on the other hand, as we're going from gas to liquid to solid, we have to remove energy. And what's happening is we're trying to re-strengthen the attractions between our molecules, those intermolecular forces, in order to take us back down to the liquid and solid state. So this is where we're strengthening the attractions, moving to the left. And so let's kind of look at this for a second here and see if we can determine how these weakening or strengthening attractions affect phase changes. So here's another simulation. All right, so here again, what we can control are the strength of attractions. But now we have a new button this time, which is going to allow us to manipulate the temperature. And so let's start out with some strong attractions. All right, so strong attractions, very similar to our solid state. Now let's pretend that we want to overcome some of those intermolecular forces and take this substance into the liquid state. If we need to break those forces, we're going to need to add energy. So let's go ahead and start increasing the temperature. Now I want us to note the temperature value at which we start to see some characteristics of a liquid. So maybe kind of right here where some of the things are moving around. So that's about a temperature of 1100 Kelvin, okay? So what we're seeing so far, we can just kind of take a few notes here, is that when the attractions are strong, we first go to a liquid at about 1100 Kelvin. Let's see what temperature it takes us to get to a gas. All right, let me clear my pen here. Okay, so it looks like to kind of fully get to a gas, maybe 3,500, something like that. We'll kind of estimate 3,500 Kelvin for our temperature. So let's take note of that. So to reach a gas, we had to raise the temperature to about 3,500 Kelvin. So higher temperature means higher energy. Now let's investigate or compare what happens to those phase change points when we have weaker forces. So in going to a liquid, that's representing the phase change of melting. And when going to a gas, that's representing the phase change of vaporizing or boiling. So let's change our settings here and see what we find. So reset. But this time, let's start off with very weak attractions. And let's notice if it becomes easier or harder to make these phase changes. All right. So we're starting off low temperature, low attractions, still in the solid state. Now again, let's notice the first temperature where we start to have more liquid character. Okay, so I'm saying maybe about 320 Kelvin. So let's make note of that. So for our weak attractions, we only had to raise the temperature to 320 Kelvin to get it to melt, quote, quote, to a liquid. Now that's interesting. Let's see if the same pattern holds true for transitioning to a gas. All right, so let's look for the first sign of kind of full gas. All right, maybe here at 1300. So let's make note of that. Wow, that is a substantial difference. So we see that when our attractions are weak, it is a lot easier for them to move into liquid and gas phases, because liquids and gases have weaker attractions than does a solid. So what the pattern is that the stronger the forces, the more difficult it is to melt or boil the substance. The more difficult that change, the more energy you're going to have to apply to overcome the forces. What that does is results in a higher melting point and a higher boiling point. On the other hand, when the forces are weak, it doesn't take as much energy because there aren't as many forces to overcome. So weaker forces result in lower melting points and lower boiling points. So let's add this to our notes. Alright, so what we found via the simulation is that the substance with the highest boiling point requires the most energy to change from a liquid to a gas. This means that its intermolecular forces are the strongest. Now on the flip side, the substance with the lowest boiling point requires the least amount of energy to change from a liquid to a gas. This means that its intermolecular forces are the weakest. Alright, and that kind of makes sense based on what we saw in the simulation. So now let's see if we can make some further connections by looking at some experimental data. We've got 4 substances here that all fall into the classification of alkanes, meaning they just involve single bonds to carbon and hydrogens. And I'll draw out the Lewis structures to help you guys see them a little better. So we've got methane, which is CH4. That looks like this. We've got ethane, which is C2H6. So we've got 2 carbons now. That's interesting. Then the next molecule, which is propane, has 3 carbons, 1, 2, 3, and 8 hydrogens. Get those guys in there. And then the last molecule, butane, has 4 carbons and 10 hydrogens. So let's draw in all of those bonds. All right, almost there. It's got a lot of bonds. All right, there we go. So now let's make some observations. What we notice is that butane has the highest boiling point. Now, think with me just for a second. I know when we have negative numbers, that kind of flips what high and low means. So look down on this chart for me. When you're in the negative region, the closer your values get to being a positive number, that indicates a higher boiling point. So for example, -1 up here is a higher boiling point than -162 down here. So what we're seeing is that butane has the highest boiling point and methane has the lowest boiling point. Now what we know just from our simulation is that the highest boiling point means that that substance, butane, would have the strongest intermolecular forces. On the other hand, the substance with the lowest boiling point, methane, would have the weakest intermolecular forces. Now let's look at this graph and kind of our drawings and see if we can figure out what structural factor could be responsible for this wide range of boiling points. And so even though they have the same types of atoms, what could be causing stronger forces? So what we notice on our graph is that on the x-axis they're measuring the number of carbon atoms. And so what we see, as you add more carbon atoms, the boiling point goes up, which means the forces are getting stronger. So it looks like as our molecules get bigger from adding more carbons, the forces get stronger. So maybe that's the factor that's at stake. So what we're going to put is the size of the molecules seems to be affecting the forces, which in turn affects the boiling point. So the size of the molecule, and specifically here the number of carbon atoms. As you add one more carbon atom, the molecule kind of grows. Now what we're going to find is that this effect of the size of your molecule is actually going to have a specific name to it. It's going to be a specific type of intermolecular force. So this leads us into a discussion of, well, what are these forces exactly? And so what we're going to find for our purposes is we're going to cover 3 different types of intermolecular forces. There's London dispersion forces, dipole-dipole forces, and also hydrogen bonding forces as well. And so I'm going to put this in parentheses. Now remember, even though hydrogen bonding has the word bonding in it, we're still talking about intermolecular forces between molecules, not a bond within a molecule. So it's a little misleading, but we'll talk about that in a second. All right. So now we want to take a look and kind of fill in the chart to help us compare and contrast these 3 different types of forces. So let's start off with London dispersion forces, which have to do with size. So what we were looking at in our data was actually an example of how London dispersion forces apply. And the words we've got in parentheses here, van der Waals forces, is sometimes another name you'll hear, but we're going to stick with London dispersion forces just for consistency. Now, London dispersion forces, they occur between all molecules, all right? And so what causes these types of forces are the random movement of electrons. I'm going to use the symbol E- for electrons, that creates what's called temporary dipoles. And what we're going to find is that the more electrons a molecule has, the stronger the London dispersion forces. And you'll sometimes see those abbreviated LDF. And so here's how this kind of works. So I'm going to take you to a little quick video right quick. Here it is. All right. So what we're going to see is that even though we haven't talked about electrons a lot, all molecules have what's called an electron cloud that kind of surrounds them. And what can happen is when 2 molecules with electron clouds get close to each other, their clouds can kind of temporarily shift to create a dipole. This is similar to what you talked about with polarity, where one of the atoms has greater electron density, so it's going to be more negatively charged. Another one of the atoms has less electron density, so it will be more positively charged. And this is due to them kind of getting close enough to temporarily shift their electron clouds to create just a moment of attraction. But you'll notice this isn't a permanent effect, and then they separate and kind of go on their way. So that's where the word temporary comes into play. Now with bigger molecules, these electron clouds are going to be bigger, and so we're going to see a bigger effect. And so that's why London dispersion forces are size dependent. Now out of the 3 forces that we're going to cover, these London dispersion forces are generally the weakest. But we're going to leave ourselves a note here that says, however, when you have really big molecules, they're going to have a good bit of London dispersion forces. And so sometimes that can overcome some of the other forces although London dispersion forces are typically the weakest. So these are size-dependent forces. All right. Now it says, does the presence of this intermolecular force indicate that the substance will have relatively high melting and boiling points? So, generally, no. If you have a weak force, it doesn't tend to affect the boiling point and melting point significantly. All right. Then it says, does the presence of this intermolecular force indicate that a substance will likely be soluble in water? And so, generally, the answer is no here as well. And so what some of you guys talked about, depending on what lab activity you did, is for substances to dissolve in water, they need to be similar to it. So when you have water molecules are very polar, and typically things that have London dispersion forces are not as, or things that have significant London dispersion forces are not as polar. And so we'll kind of come back to this category once we compare the other forces. Now, an example of where this might occur is perchance a sample of helium gas or methane. So let's draw just a little diagram kind of right quick. So what happens is, let's do our helium first. And so let's pretend that you've got two helium atoms that are close together. They've both got an electron cloud. Now what can happen is one of the helium atoms can temporarily shift its electrons toward one side. What this does is makes this side of the helium molecule more negative. Now, we know that opposites like to attract, so what the other helium molecule will do in response is shift its electrons to the other side, and that creates a more positive side right near the negative side of the first helium. And so this creates a temporary London dispersion force attraction. The same thing would work with CH4. So this is a bigger molecule, so we're going to have room for a larger electron cloud, which means more of these London dispersion forces going on. All right, there we go. So again, maybe this molecule on the left is able to shift its electrons temporarily, and that creates a more negative charge here. So the other molecule in response is going to shift temporarily its electrons to create a more positive side that will be able to interact with the more negative side. But that larger electron clouds leads to larger London dispersion forces, more powerful interactions. Now, let's go back and talk about the two other forces, dipole-dipole forces, and then finally, hydrogen bonding forces. All right, so dipole-dipole forces, the name kind of gives us a hint. These are forces that occur between only molecules that are polar. London dispersion forces, however, those occur between all molecules, even those that are non-polar. All right. And so what happens to create a dipole-dipole forces is you have attractions between the charged dipoles of molecules. And I'm going to insert the word permanent here just to contrast with the temporary dipoles from London dispersion forces. And so just to kind of illustrate what this means right quick, let's go down and go ahead and do our diagram. So an example of where you might see some dipole forces is with a sample of HCl or HC or H2CO. Now let's look at both of these molecules. We learned from our polarity lesson that chlorine is more electronegative than hydrogen, so its side will be slightly negative, while hydrogen's side will be slightly positive. This is known as a permanent dipole because that's just an inherent characteristic of the molecule based on the electronegativities of its atoms. So here's what's going to happen. If another HCl molecule comes nearby, it's going to orient itself so that opposite partial charges can align. So the positive hydrogen on the second molecule is going to want to interact with the negative chlorine of the first molecule. And so what this does is creates two sets of interactions. You have a dipole interaction here and a dipole interaction here. That's why this force is known as dipole-dipole. Let's also take a look at this with our second molecule, H2CO. And I'm going to kind of draw this one sideways. Oops, and let me not use organic notation, so that's for chemistry too. Alright, so here oxygen is the most electronegative, so he'll be more negatively charged, and this carbon and hydrogen side will end up being more positively charged. So this is a polar molecule, so if it were to interact with another one of these same molecules, they would align in order to allow those opposite charges to line up and interact. So what we would get is an interaction between that negative oxygen side and the positive hydrogen and carbon side. So again, you've got dipole-dipole forces, the dipole of one molecule interacting with the dipole of another molecule. And as long as the molecules are polar, they can do these types of interactions. So now, if we are comparing the strength, dipole-dipole forces are kind of somewhere in the middle. So we'll call them medium strength. They're stronger than London dispersion forces, but we'll soon find that they're weaker than hydrogen bonds. And so if a substance has dipole-dipole forces, sometimes or somewhat that indicates that they're going to have higher melting and boiling points. Then it says, does the presence of this IMF indicate that a substance will likely be soluble in water? And so the answer here is generally yes. Since water is a polar molecule, it can also participate in dipole-dipole forces. Things that share similar forces are often able to dissolve in each other. And then we've already done our diagram. Now let's wrap up our chart here with the last type of force, which is called hydrogen bonding forces. So again, it's not a real bond, it's just a very strong type of force. And so where hydrogen bonding occurs, zoom in here for you guys, is it occurs between molecules that have hydrogen. So molecules that have hydrogen directly bonded to fluorine, oxygen, or nitrogen. So kind of a little acronym, FON. So it's FON to hydrogen bond. If that helps you remember it, by all means, have at it. All right. And so this type of force is similar to dipole-dipole forces in that it results from kind of strong permanent dipoles. And so as a result, this is going to be, in general, the strongest force that we encounter. And so let's go ahead and give an example right quick of what we mean by having hydrogen directly bonded to F, O, or N. So an example of this would be water, or we can look at NH3, ammonia. So if we consider a water molecule, we know it has a bent molecular shape, and we know that it's polar, that oxygen is more negative and the hydrogen is more positive. Now if we look on the periodic table, these three elements, fluorine, oxygen, and nitrogen, are at the top right-hand corner. Now what that means is that these are the most electronegative atoms. And so the more electronegative, the better they are at pulling electrons to themselves. So this creates kind of a really large partial negative on oxygen, fluorine, or nitrogen. On the flip side, what that does is create kind of an equally large partial positive on the hydrogens. And so what happens when another water molecule comes along, the lone pairs on this water molecule are going to be attracted to that large partial positive on the hydrogen of that first water molecule. So this is representing a hydrogen bond where you have an interaction between a hydrogen directly bonded to oxygen and the lone pairs of another highly electronegative atom. And we could continue this if you had more than two water molecules. You could repeat this interaction throughout. And so again, it's just a strong force of attraction due to those large partial negative and partial positive charges. Now let's look at it with NH3 right quick as well. So I'm going to draw it upside down just to kind of give you guys some different perspectives. So again, since nitrogen is highly electronegative, it'll have a large partial negative and a large partial positive on the hydrogens. If another NH3 molecule is in the container, they will be able, the lone pairs on that NH3 will be able to interact with those positive charges, large partial positives, on those hydrogens. And so it's those large partial positives along with the lone pairs that create this really strong interaction known as a hydrogen bond. And so I want to take you to a quick simulation to illustrate this right quick. Let's see, here it is. And so it's going to show you kind of in the little dashed lines here, it will show you the hydrogen bonds. Now if I slow these down a little bit, you'll be able to see those dashed lines a little better. And so you'll notice that these aren't the same as a bond within a molecule. They're forces of attraction, but they're pretty strong, so they're still holding those molecules together more tightly. Now I can go ahead and turn on the partial charges, and you'll always see that these hydrogen bonds align so that the positive hydrogens are attracted to the more negative oxygens with those lone pairs. And so here's kind of slow motion where you can see those hydrogen bonds at play. So again, they can be separated. It just takes a good amount of energy since they are a strong force. Alright, so let's finish up our table. Y'all are doing great. I know this takes some time to get through, so hang in there. So the next question we encounter is, does the presence of this force often lead to high melting and high boiling points? And the answer here is yes. Since hydrogen bonding forces are strong, they typically require more energy to overcome to get into the liquid or gas phases. Then finally, does this indicate that water or this substance will be soluble in water? Generally, yes. Water can also hydrogen bond, so other things that hydrogen bond generally mix or dissolve in water pretty well. Now, here's what it really takes to kind of get this down pat, and that's just some good old practice problems. So since we're not here together in class, we're going to walk through several practice problems together with me before you practice on the homework module on your own. So here's just a little brief summary. So our three types of forces from strongest to weakest are hydrogen bonding, the medium strength force are dipole-dipole forces. And then finally, the weakest forces are London dispersion forces, or also abbreviated LDFs. And so in general, the stronger the intermolecular forces, the more attracted the molecules are to each other. And this tends to result in a higher boiling point. In general, the weaker the intermolecular forces, the less attracted the molecules are to each other, which results in a lower boiling point. Less attractions means easier to separate. Okay, so the first kind of number one here is just going to have us go through and look at some different molecules and list which of these three forces are present. Then we're going to underline the intermolecular force that is the strongest. Now on these, it's important that we have kind of good Lewis structures to go off of. So I'll be drawing those for us as we go. So here is HBr. And now within our forces, every single one of these molecules is going to have London dispersion forces. So out of our list, London dispersion forces is always going to be a yes. Then the other three forces we'll need to check for. And I'm going to abbreviate hydrogen bonding by saying H bonding. So every molecule has electrons and therefore will have LDFs. Now we need to check to see if it has dipole-dipole forces. For it to have dipole-dipole forces, the molecule needs to be polar. So let's examine the difference in electronegativities between hydrogen and bromine. Bromine is way over here. Hydrogen's on the left, so yes, they will have a difference in electronegativity. Bromine is more electronegative. It will be partially negative. Hydrogen is partially positive. So yes, we do have dipole-dipole forces. Now let's check on hydrogen bonding. What we need is a hydrogen directly attached to something fun, fluorine, oxygen, or nitrogen. Here, hydrogen is attached to bromine, so no, this molecule does not participate in hydrogen bonding. So it does have LDFs and dipole-dipole forces, but no hydrogen bonding. Out of the two forces that it has, dipole-dipole forces are the strongest. All right, let's go to our next molecule, which is I2. Okay, so we've got our three forces: London dispersion forces, dipole-dipole forces, and hydrogen bonding. Let's check to see which forces it has. We know that all molecules have London dispersion forces, so we can immediately check that one off. The next question is the molecule polar? Well, not quite. Since iodine is the same thing as iodine, there's no difference in electronegativity, and this molecule will be nonpolar. If it's nonpolar, then it cannot have dipole-dipole forces. And what we're going to find is that nonpolar molecules can also not do hydrogen bonding. We don't see any hydrogen here, and it's not attached to F, O, or N. Alright, now let's look at our good old water molecule. So we've got H2O, there's our lone pairs. So we know it's going to have London dispersion forces. All molecules with electrons do. So that's good. Now let's check for dipole-dipole forces. And so the question we have to answer is the molecule polar? Yes. Oxygen is more electronegative than hydrogen. That creates a separation of charge. So yes, we will have dipole-dipole forces. Next, let's go ahead and look at hydrogen bonding. What we need is a hydrogen directly attached to oxygen, fluorine, or nitrogen. Hey, we have that this time. So yes to all three forces. So it's one thing that's neat about water is it can participate in all three types of intermolecular forces. All right. So now let's pick just a few more out of this section. Let's do F, G, and H just so we can keep moving. So let's look at F. We've got carbons and hydrogens. And if we think about the shape of this, those are kind of going to be two tetrahedrals joined together. We already know that all of our molecules will have London dispersion forces. But now, when we're checking for dipole-dipole forces, we need to ask the question of whether or not the molecule is polar. Now, hydrogen and carbon have very similar electronegativities. And when they're also arranged in a tetrahedral shape, this is going to result in a non-polar molecule overall. There's no negative side and positive side, but charge is distributed evenly. So if they're non-polar, there's no dipole-dipole forces. Now, even though this molecule has hydrogen, it is not directly attached to fluorine, oxygen, or nitrogen. So no hydrogen bonding there. And so the only force present in nonpolar molecules are London dispersion forces. All right, let's get NH3 right quick. So get a quick Lewis structure. And remember, if you need to kind of slow down and think or write, you're welcome to pause the video at any time. So let's check this out. We know that NH3 is a molecule with electrons, so it will have London dispersion forces. The next question we need to answer is the molecule polar? Nitrogen is more electronegative than hydrogen, and due to those lone pairs, this takes on a trigonal pyramid shape, which kind of creates a top side that is negative and a bottom side of the pyramid that is more positive. So yes, the molecule is polar. Yes, it will have dipole-dipole forces. Now let's look at whether or not it will have hydrogen bonding. We do have nitrogen directly attached to hydrogen. So FO or N, we have the N. So yes, this will participate in hydrogen bonding as well. All right, last one from this section. Y'all are doing great, guys. So we've got London dispersion forces. We've got dipole-dipole forces. And then our last force is hydrogen bonding. And I realize I've been forgetting to underline the strongest force. So let me go back right quick. So for iodine, the only force it had was London dispersion forces. So that's its only and strongest force. For H2O, its strongest force is hydrogen bonding. For our C2H6, the only and strongest force was LDFs. And then for our last one, because it had all three forces, hydrogen bonding will be the strongest. Now let's take a look at this next one. We know it's going to have LDFs, like every other molecule, but now we have to answer the question, is it polar? So immediately when I see those oxygens, that lets me know that this side is going to be more negative, while the side with my hydrogens and carbons are more positive. This has created a separation of charge, so the molecule is going to be polar. So yes to dipole-dipole. Now let's take a look at hydrogen bonding. And so we have to ask the question, is hydrogen directly bonded to fluorine, oxygen, or nitrogen? It is. So we will have hydrogen bonding in this molecule. Out of those three forces, hydrogen bonding is the strongest. So in this first section, we were just practicing identifying the basic types of IMFs present within a given sample of molecules. So now we're going to try to start using our understanding to explain some differences in phase changes. So it says, use our understanding of intermolecular forces to explain why CHCl3 boils at 61 degrees Celsius, while CHBr3 boils at 150 degrees Celsius. So let's draw these out and see if we can find any patterns. So there's CHCl3. I'll be a good example and put my lone pairs in there. And then here's CHBr3. Again, we're following that pattern where carbon has 4 bonds. Now, what we're going to notice about both of these molecules is they're both going to be polar, where the top region with bromine and chlorine is more negative, and the bottom region with hydrogen is more positive. So they both are going to have, dipole-dipole forces, and they're also both going to have LDFs. So let's start just by listing the forces that we know they have. So they both have dipole-dipole forces, and they both have LDFs. Now, what they told us is that the molecule with bromine boils at a much higher temperature than the molecule with chlorine. And so what we have to think about is a higher boiling point means stronger intermolecular forces. So let's see if we can remember anything about LDFs. So when we were taking notes, we talked about how London dispersion forces were dependent upon the size of the molecule. So let's go to our periodic table and see if we can figure out any patterns. So y'all don't know this quite yet, but the farther down on the periodic table you go, the bigger the atoms get. So bromine, since it's farther down than chlorine, is going to be a much bigger atom. So what that means is that this molecule with 3 bromines is going to be bigger than a molecule with 3 chlorines. And so the difference here is going to be the strength of the London dispersion forces. Because bromine is bigger, that molecule will have stronger London dispersion forces, resulting in a larger boiling point. All right. So now let's look at this next one. It says which molecule would have the lowest melting point? CCl4 or CS2? So here's CCl4. And here's CS2. And actually, I'm looking at my time now, and I'm getting close. I'm about 10 minutes away from an hour. So I tell you what, let's go ahead and skip to C, because I do want to get to the last couple of practice problems, and that'll keep us hopefully right at an hour. So sorry, we're going to skip B actually and just go straight to C. All right, so it says dimethyl ether, that's this guy over here, boils at negative 25 degrees Celsius, whereas ethanol boils at 79 degrees Celsius. How can we account for this difference using intermolecular forces? All right. So anytime you get one of these questions, it's a good idea to list out what intermolecular forces you see. We know both of them will have London dispersion forces, and they've got an oxygen there, so we can decide that these are probably going to be polar molecules as well. And keep in mind that these dimethyl ether here, that oxygen has lone pairs which kind of bends the molecule into a V. So they both have London dispersion forces, and they're both going to have dipole-dipole forces. Now let's look at hydrogen bonding. You'll notice that both molecules have oxygen and have hydrogen. However, only ethanol has hydrogen directly bonded to the oxygen. So ethanol is the only one of these molecules that has hydrogen bonding. So what we see is ethanol, due to that presence of hydrogen bonding, is going to have stronger forces, which results in a much higher boiling point. So that's crazy. It boils at almost 80 degrees Celsius, whereas the other one boils at negative 25. So it's a much lower boiling point. So that presence of hydrogen bonding creates stronger intermolecular forces, resulting in a higher boiling point. All right, so let's finish up here with 4, 5, and 6. And I'm going to attach my little screen here. That way we can type out a more thorough answer for these. All right. So, sorry, I'll take you back here. All right, so this one says sulfur dioxide and nitrogen dioxide both have dipoles. So that means they're both polar, in other words. And then carbon dioxide, or carbon tetrafluoride rather, is nonpolar. All the molecules have relatively similar masses. What could account for the difference in their boiling points? Okay, so we know that if all that carbon tetrafluoride has is LDFs, that explains why its boiling point is so low. Weak forces have a low boiling point. Now, when it comes to nitrogen dioxide and sulfur dioxide, it told us that they have about the same mass as carbon tetrafluoride. If the molecules have the same mass, that means they're all about the same size. So their London dispersion forces should be similar. But they did tell us that nitrogen dioxide and sulfur dioxide were polar. And that explains why both of their boiling points are higher than the nonpolar carbon tetrafluoride. Because they're polar, they're going to have dipole-dipole forces. But we've got to figure out now, why does NO2 have stronger forces than SO2? So let's kind of take a look at this right quick. So we've got SO2 here, kind of just briefly sketch it out. NO2. All right. Now if we look on our periodic table, we're going to notice that oxygen is is 1 square further to the right than nitrogen. So what this means is oxygen is more electronegative. So if oxygen, or excuse me, we're looking at nitrogen and sulfur, aren't we? My apologies here, because both of them have oxygen in common. So let's compare sulfur and nitrogen. All right, so one more again. So here is sulfur, and here is nitrogen. Okay. So if we compare those positions on the periodic table, we know that nitrogen is one of our highly electronegative atoms, right up there with fluorine, oxygen, and nitrogen. So since nitrogen is more electronegative, it's going to create kind of bigger negative and positive charges. Since sulfur is less electronegative, it's going to create smaller negative and positive charges. So what that means is that the molecule with sulfur must have weaker dipole-dipole forces than the molecule with the nitrogen. So what we can tell from this is that since the boiling point of NO2 is higher, it must have a stronger polarity, resulting in stronger dipole-dipole forces. All right. Now let's finish up with this last one here. Boiling point trends for hydrides. So we've got a graph and it shows the boiling points of various substances. And it asks, does SiH4, so that's right here, or CH4 have the stronger intermolecular forces? Explain how you know based on the graph and what you have learned about intermolecular forces. All right, so if we look at our graph here, what we are noticing is that SiH4 has a higher boiling point than CH4. Again, remember, as you get closer to the positive numbers, your values are getting bigger in terms of boiling point. So if SiH4 has a stronger or a higher boiling point, it must have stronger attractive forces. All right. So we'll say since SiH4 had the higher boiling point, it must have stronger intermolecular forces. A higher boiling point indicates stronger attractive forces between molecules. So we're using what we see from the graph, a higher boiling point, and connecting that to stronger forces between molecules. Now, the last question it asks us about the graph is it says the trend in the data between the first and second molecules in group 14, so that's this blue line, is different than the trend in the other groups. So you'll notice for the other groups, the first atom or the first molecule that's listed starts out at a much higher boiling point, then it drops. However, for the blue line, it kind of goes up steadily from CH4 to SiH4. And it says, how can you explain this difference in terms of intermolecular forces? So what we need to do is to compare our starting atoms and see if there's anything that we notice about their forces. One thing that I'm immediately picking up on is I see nitrogen, fluorine, and oxygen. So all of these molecules have hydrogen in common, but what's separating them is the atom that hydrogen is attached to. So in these first three, hydrogen is attached to something very electronegative, while in the last molecule, it's just attached to carbon. Okay, so if hydrogen is attached to fluorine, oxygen, or nitrogen, that means that they can hydrogen bond. If we look in group 14 on the periodic table, which is right here, none of these atoms in the group are capable of hydrogen bonding. You have to have either fluorine in group 17, oxygen in group 16, or nitrogen in group 15. So what we see in this last example is that group 14 contains no atoms that are capable of forming hydrogen bonds. Therefore, all of the molecules in that group only have London dispersion forces, which will increase with molecule size. So due to that lack of hydrogen bonding, we see kind of just a steady increase. However, with the hydrogen bonding, that's a much stronger force and a much higher boiling point. All right. So, you guys have been such troopers during this lesson. Again, learning is not a one-time process, and so we don't expect you to necessarily get everything this first time through. So feel free to use the recording to go back and re-watch, to slow down, to re-practice some of the practice problems. And then also make sure as you do your homework module that you make note of any questions you have and take them to your teacher in office hours or via Schoology Messenger. That way they can help you kind of come to a better understanding before you take the quiz. So thanks so much. You guys have a fantastic day.